This program, you can start here saying it's a new mechanism, and then it's going to load by default some settings. And with these settings, the first thing that you have to do is to define the general characteristics. And the general characteristics, now we're going to see what is the mechanism we want to perform, to simulate, and there we have it. The mechanism is a sieving mechanism that we're going to check how many, because it's asking us how many solids that it has, how many links it has, and then the number of actuators and the number of forces you want to perform the analysis. And then you can set up, if you want, gravity with its constant that is already defined, or don't use it for the simulation. So what I'm going to use is lab session, for example, lab session 4, and now I'm going to count the number of bars that this one has. So I can see bar 1, 2, the thread puller, 3, the flywheel, 4, bar 2, and then 5, the needle. If you go down, you will see that you have these 5 solids here, and then also you also have the frame. In this program, you have to also upload the frame in order to see where these points are connected, because you need this relative distance in order to be able to solve the simulation. Then, a first step that is very useful after counting the number of solids that you need is, and we're going to perform later, is in this same picture, try to draw the coordinates, the local coordinates that we want to use for any of these solids. But first, let's set up the number of solids. So as we said, we have 6 solids and how many links. And here it's said, okay, you have to include here the frame. So that's why we put this 6, 5 plus 1, 6. And then here you also have to include a link that is the frame linked in the space. So in order to make it fixed, because if you didn't make this is restricting, giving you a restriction of 3 degrees of freedom into D in order to set up where has your frame to be located in space. Then we're going to count the number of links. So we have 1, 2, 3, 4, then 5, 6, 7 with the needle, and then plus 8th one that is this fixed links to the with the frame. So we're going to have 6 plus 6 solids plus 8 links. And then the number of actuators is going to be the number of degrees of freedom that we have. And if you want to count here, you're going to see that you have only 1 degree of freedom. Okay, then when you say accept, it's going to write down what you have inputted in the first window. Then the next step is going to be setting up where do you want to have the local, first the global triad and then the local ones. So what I'm going to do is I'm going to draw on paint this local triader and the global one. So I'm going to choose this point to be my global one. Okay, no, I want the pencil. Okay, so here is going to be my global one, and then my local ones. I'm going to be intelligent in order to make it be the same one whenever I can. For example, on the frame, I'm going to set up my local 3 header here, and then on the bar 1 also here. Then for the thread puller, I'm going to put it here. On the bar 2 here. On the flywheel, I'm going to put it where will be easier. I think, yep, this one is here. And on the needle, as you only have 1 point in this single point. Because now the program is going to ask us each solid how many points and how many lines does it has. The points and lines are only set up in order to establish links between them. So we are going to count the number of points and the number of lines that we have in each solid. I'm going to use blue. So in the frame, how many points do we have? We have this point because we need a revolving link here, another one here, and then a line here. Because we're going to need a link here in order to carry the needle movement. Again, on bar 1, we're going to have only 2 points. Here, another one here. In the thread puller, we only need 2 points because it depends. If you want to study the movement of these points, then you will need to define another one, even if it doesn't have a link here. But the only 2 that you need in order to simulate the whole movement of the mechanism is going to be those 2. So right now I'm going only to define those 2 in order to simplify the exercise. For the bar 2, also these 2. For the flywheel, we need 3. And then for the needle, we need 1 point and 1 line. Okay, set that. We're going to put these inputs in the next window. This definition, solids. And then we're going to have solid 1. That is going to be the frame. How many points we said it has? So we said it has 2 points and 1 line. Okay, then 2 points here, 1 line. If you want to make your simulation more complex, you also can define your mass and your moment of inertia. But for this exercise, we're not going to do it. Then next one is going to be bar 1. And bar 1 is going to have 2 points. Then up bar 2 is going to have also 2 points. Come on. Then the thread puller is going to have also 2. Then what else do we have? The flywheel. The flywheel is going to have 3. And the needle is going to have 1 and 1 line. Okay, everything is correct. Then go. Then, what do we have to define right now? Where are the points located? Locally. So on the local triad. So for example, for the frame, what do we have? On the frame, we define this as the local triad. So point 1, I'm going to say, this is my point 1 from the frame. This is going to be point 2 from the frame. Okay, and then here bar 1, I'm going to say, this is bar 1 for the bar. What I'm going to do is to make a global name in order to make it easy to follow. So this is going to be my 1. my 2, 3, 4, 5, and 6. Then, okay, this is 1, 1, 3. This is going to be 3, 2, 3, 4, and then on bar 2, I'm going to have 5, and then also 6. Okay, then for the flywheel, I'm going to have a 2, 3, and a 4. And for the needle, just a 6. Okay, I'm going to try to define those solids, the points of those solids with these numbers in order to later make it easy to put them in contact. So point 1 of the frame is in 0, 0. Point 2. Okay, I'm going to define them like 1, 2. Then point 1, point 2. Where was point 2? Point 2 is located at 15 millimeters in X and 20 millimeters in Y. 15 and 20. Then for bar 1, we have point 1 and point 3, and they are with a distance of 28. Point 1, point 3. And this is going to be in a distance in X of 28. 28, yeah. The next one is bar 2. Bar 2 has the 5th point and the 6th one, and with a distance of 33. Then 5, 6, and a distance of 33. Okay, then the thread puller. The thread puller has points 3 and 4 and a distance of 22 between them. 3, 4, and I said that the distance was 22. So 22. Okay. Then the flywheel. The flywheel point 2, if I'm not wrong. Yeah, point 2, point 3, and point 4. 3 and 4. Point 2 is in 0, 0, because we defined it here, the local triad. And then at 14, we have point 4 in X. 14, we have point 4, and the point 3 is located in 11 and 6. This is a 6, or is it a 9? 9 thing. Yeah, because it's both. 11 and 9. Okay. 11 and 9. Okay, and then the needle is on the origin, but the point, I define it as 0.6. Okay, then we have defined all the points. Now we're going to define the lines. As we only have one line, I'm going to define both of them as line 1. It's the line of the needle. And then what is the distance of line 1 respect to the origin of the frame? So here we have it. Is it at the distance of 15 plus 3 in the X direction? And then as it is a line, it can be infinite in Y, so we don't need to put a Y distance. So 18 in X direction, and the angle, we don't want to keep it horizontal. So what I'm going to do is to turn it p half, and p half is going to be 1.57 if I'm not wrong. So because the original orientation of the lines are always horizontal. So like this. So in order to turn it to have this direction completely on the Y direction, what I have to do is to turn it 90 degrees. Okay, and then this is P half, and it's 157. Then for the needle, I'm going to do exactly the same, but it's located on the, it's going through the 0, 0, so I can leave it like this, and the direction, I'm going to modify it also to P half. Okay, and here it says we have defined the lines, and then we have to define the links. So first one is the link that is corresponding with the frame to the space. So it's the fixed one that it says. We're going to keep it like this. Then I'm going to call them like the points they are connecting. So one single rotating link. What I'm going to do is put frame 1 with bar 1, pond 1. Okay, and 2. Also single rotating frame 2 with flywheel 2.2. That's why it's useful to name them smartly. Then third one, it's going to be bar 1.3 with thread puller 0.3. 4.1 thread puller 0.4 with flywheel 0.4. The fifth one is going to be bar 2.5 with what is the yeah, did a mistake. Boop, boop, boop. I did a mistake because the flywheel is not well named. So what I have to do is to put here it's going to be 4 instead of 3, and here is going to be 5, the fifth point. Okay, it's good that we detected the problem soon. So in order, as the flywheel names were wrong, this one should be the third one. Sorry, third one here, and then instead of being linked with the fifth one, is going to be with the fourth. And here, okay. Then 6 is going to be bar 2, 6 with the needle, if I'm not wrong. Yeah. And then the last one is going to be the needle, the translation movement of the needle. And it's going to be a prismatic one. Where is it? Here. And then it's going to set up one line has to be coincident with the other one. And then here it's going to ask you which one do you want to be the one that is carrying the other. So that it's just for to make it visible. So here what I'm going to say is this option, and we'll see how it works. Then now, last one, the actuator. Where do you want to be the motion to be? So what the different options that you have are the one that I'm going to take is going to be the angular polynomic, because I want it to be a rotating motion. And here you see the formula that is going to use to set up this movement. And between which solids do we want to do it? Between the frame and one that has to rotate 360 degrees. And which one is this one? The only one that is doing the full 360 degrees is going to be the flywheel. So we are going to set up this with the flywheel. And then this is going to be what is our initial angle, what is our speed, what is our acceleration, and what is the derivative of the acceleration. Right now, I'm only going to set up as a constant speed. So for example, here, I'm going to put a 1. So right now, our mechanism is going to evolve following a constant speed of 1 radian per second. Okay, then I accept, and now I'm going to try to set up the mechanism. Probably is going to fail, and it is expected to fail because right now, if you think about it, we are inputting all the parts together in a single point, and with initial coordinates, we're going to be able to put them in relation with the global set point that we are going to set up. So we are going to be able to set up all the parts in relative distances with this point here. Okay, then we're going to say we're going to try it, and it says that the system is not able to set up. Okay, because you can see all the mess that we have done. Frame, we're going to see that I did an error because right now our 0 is defined here, but you can see that the shape of our mechanism, we set up here the 0, and the second point should be below the first point. Why does this happen? Because I forgot to put this distance in negative. So I'm going to show you how you can solve this problem. And what you have to do is go to definition again, and then in points, redefine the second point and set it up as -1. Okay, then I'm going to try to set it up again. All the distances. Okay, then now it looks much more what we wanted to have. Then, okay, first one that we can move. This is usually the most complex one, the most complex part to solve this kind of simulations. For example, we're going to move the flywheel. We are going to move the origin of the flywheel here to set up at this point on the global triaeder, and it's going to be, we're going to move it 15 to in the x direction and -20 in the y direction. Then, okay, flywheel 15 and then -20. And then if we say pre-visualization, it moved here. Okay, nice. Then what else can we move easily? For example, we want to move we're going to set up, for example, the thread puller. We're going to move it from here, that is right now. We're going to move it this 28 distance in order to make it coincide the third point, make them, both of them, be at the same place, or at least close to it, because the program doesn't need it to have it exactly at the same place, but it has to be close in order that he can solve the position equations in order to set everything up. Then, what was the distance? It is 28 for the thread puller in x direction. Okay, 28. Okay, you can see it moved here. And then But now, as you can see, it is in horizontal, and the thread puller in this configuration is more or less vertical. So I'm going to turn it 90 degrees. Okay, 90 degrees is 1.57, but now it's up, so it's on the other direction, negative. Okay. Then, what else do we see here? The thread puller should coincide with this 0.4 of the flywheel. So what we can do is rotate a little bit and the flywheel to be closer to this point. Okay. And this we are going, for example, to set here -1. And this seems a little bit too much, so I'm going to try with -0.9. Okay, now this is a little bit closer. Then, what else do we need? Here I see I have another error, I think, because I don't have a link here, and I should have it. I'm going to see what happened here. On the flywheel, I have 0.3, 0.2 setups, 0.2, flywheel 0.3. And here I see I did an error here, and I choose the thread puller instead of the flywheel that it should be. Because if you remember, flywheel 4 was 5. Okay. And then, okay, now you see that this link appear here saying, okay, you have to link it with something. And this something has to be bar 2. So I'm going to select bar 2, and that right now is horizontal here. I'm going to make it go down in order to coincide more or less with the 5th point of the flywheel. So it has to go 20 down and more or less, let's say 15 plus 14, let's say it goes 28, right? Because this will have an angle. We're going to set it up little by little. Okay, then -20, 20, and not the other way around. 28 and -20. So it went here. So we need it to go this distance down. That is going to be, for example, I don't know, 28 to, no, a little bit more, -32. Okay, more or less. And then on the X direction, I went a little bit too far, and I'm going to try with 26. No, 24. Okay. And then I'm going to set it up looking down, -1.57. Okay. Now it looks more or less like the picture of this setup. So now I'm going to set up the needle in this X direction in order to make it easy. So it has to be at 18. So the needle is here. It's going to be at 18. Okay, and I'm going to put it a little bit down just to visualize it a little bit better. For example, -30, something like this. No, a little bit more, -50, even more, -60. Let's see. let's say 65. Okay, now more or less everything is set up. What I can do is modify a little bit the angle of this bar tube. I'm going to make it a little bit bigger in order to make it coincide more or less with the needle. A little bit more. Okay, then now if we accept, we are going to try to assemble it, and it is done. Okay, and then now we can try, for example, an almost static simulation. Okay, and in animation you can see how it moves. Okay, I'm going to set up a little bit more time. For example, 20 seconds. Okay, see animation, and now you can see how it turns. Okay, and this would set up all our mechanism. One typical question is, how do I do, for example, to close the flywheel triangle? For closing the flywheel triangle, what you should do is to add a fourth point in that coincides with the first one, because the program only makes a line where you have between 2 points, 2 defined points. So in order to close it, for example, if you want to do it in order to make the visualization look a little bit more alike what you expect, you can, in the flywheel, you can add another point that is not going to be a link, okay? Okay, and then in definition, I'm going to set up this point here that I'm going to call it 2, for example, and I'm going to see it also on 0, 0. Okay, accept, and then now if you assemble it, you're going to see that you have this line here. And then now, okay, now you have the full triangle. Okay, and now you have set up all your mechanisms. What else can you do? You can also plot, for example, we're going to try to plot what is the Y position of the needle in function of the angle of the flywheel. So for example, here you can go to the graph and you can go, for example, to the phi of the flywheel and Y of the needle here. And then you can see the movement. The movement varies between -50 more or less to -30 something, and in negative to -68. And how many cycles does it does with the movement of the flywheel. Okay, and that will end up this example on how to set up the Lab 4 simulation for the